Yeah. So I'll start to talk about more course-related things. So the purpose of computer graphics. Anything? We mentioned a bit about it already. It's about actually taking some application and making a geometrical model out of it, and then sort of getting onto a two-dimensional screen, said very briefly. Okay. Now, as we see in this chain, this is a very high-level view on graphics processing. So basically, you have some application that leads to some sort of geometrical model that you can play around with and get into the computer. You have a rasterization step, which is basically you're going from some seemingly continuous three-dimensional object onto a two-dimensional pixelized screen. So that's this rasterization operation. And then, of course, you have a display. This is seen very, very sort of superficially. Now, application, it's quite diverse what you can use this for. So I just took in this slide on that. One thing is what you probably know, like video games, virtual reality, where you have user interfaces towards these things you make. But you can also use it in general for display of information. For example, in computational biology, if you want to look at, have some protein looks or something. Scientific visualization in general can be very useful for these things. Also just for general information visualization, to get a grasp of what something is in a much better way. Also, it's used in graphics design, those sort of things. So it has a very broad impact. So although you may have the intention for learning this for one specific thing, we could use it for a whole lot. So, have you defined yourselves in any of these? Where do you place yourself in this? Have you thought anything about that? Where you may use it? Why you signed up?
In video games, when you make them.
Yeah. Anyone else? Anywhere on this? You had some thoughts about when you signed up? What applications you would sort of were thinking about? No? Okay. Anyway, there's a broad range of applications. So it's if you learn it for one thing, you could use it for many other things as well. So it's a very useful tool. Okay, so I already talked about that. A bit more details. Usually you have some model from some database of some sort. It can be a surface of some kind, for example. And then usually approximate this by some polygons. You know what polygons is? Polygon is basically any closed curve, but consisting of straight line segments. So usually you have some dots, and then you connect them with line segments, and you get some sort of shape. Of course, there's a whole variety of shapes you can get from polygons. The most simple one, of course, is just a line between 2 points. One we will sort of it most often is basically the simplest closed loop you can have with some area within it, which is a triangle, basically. Because OpenGL, which is the framework, will use basically draw three things. It's points, lines, and triangles, and varieties of those. And with these triangles, you can of course make other shapes, like you can make them like that, or you can make squares, or if you have enough of them, you can basically tessellate this surface with them and then describe it in this way. Of course, when you make a scene, you always have a lighting, like in this room and so on and so forth. To make this look natural, of course, you have to take that into consideration. Which sides of your object is lit up? Is it transparent? Is it just reflecting light? Is it opaque? Those sort of things. So you need to think about that. Also, what sort of light do you have? Sunlight? Do you have some light in the living room? Then we have different temperatures and so on and so forth. You can model a lot of things here. As well, viewing transformation. You're taking a 3D scene and you're gonna project it onto a two-dimensional screen, basically. And this is, for example, I like to use the example of your eyes. Right? Your eye is basically one of the devices that is doing this from 3 dimensions to 2 dimensional onto a it's not exactly flat, but your retina is basically a 2-dimensional screen, if you like. And when you do that, you will have certain geometrical distortions. Certain geometrical features will look different from different angles, and so on and so forth. For example, if you look at this table from above, it will look like a rectangle. If you look at it from the side, it may become more like a trapezoid and those sort of things. So depending on your point of view, these objects will look different, and that you sort of have to make look in a natural way, basically. So a large part of this course will also be about these sort of transformations, and of course how you model this part. So these 3 things will sort of be a large chunk of the course, which will go into details on each and every one of them more in the coming weeks. Then you have this thing, of course. Sometimes when you have objects moving in space, sometimes they will be outside the screen, sometimes the whole object will be inside, but what's outside is not really interesting, so you basically clip it to fit to whatever screen you have, which may be inside some window on the screen. These are not so important for us here, we will deal more with these operations. Any questions? Okay, so we already talked a little bit about the key purpose and steps, creating 2D and 3D images and scenes and display them on the screen in 2D. Also, of course, integrate with conventional softwares and games, applications, other programs, and so on and so forth for illustrating information or whatever. There are, of course, some big challenges with making such models on the computer. Can you try to identify some of them? What do you think are challenges? No challenges? Okay, keyword. Variety of hardware. Different platforms. Different CPUs and GPUs. These are challenges. Different display devices. Can you think of any other challenges there maybe? Now I talked about the hardware, what about the software?
The operating system.
Exactly. That's something we're going to struggle with here. So the software varies. Different operating systems. Programming languages. You can also use different ones. We will stick to C++. Just to, I know it's taught in the basic courses here, and it's also, very nicely going together with OpenGL. It's a possibility to use it there, so we will basically stick to that. So I guess you all know C++. Anybody who doesn't? You don't? Okay. There will be a session on C++ next Thursday. But what background do you have? C? Okay, but then it should be okay. So there will be a session on C++ next Thursday. So okay. This is also a challenge. When you model some geometrical scene or some scene in general, you think in terms of models, scenes, and objects and movements of these objects in the scene. You don't really think in what is presented in the machine or the screen, which is pixels and polygons. So there needs to be some sort of translation there, going from these models to think about and then being able to present them. That's a challenge. Performance can be quite heavy. These applications, some of them. This is why I encourage you to start to think earlier about how you make things as simple as possible in the sense of eating as few resources as possible, identifying bottlenecks and so on and so forth, because although computers have a lot of memory and processing power today, some of these applications may be able to kill it anyway. So these are things to consider, and if you start to think from that in the beginning, it's just easier to catch on. It becomes a habit rather than being wasteful. You try to save. yeah, so we need a framework that automates this translation, basically. Okay, so what do we need to know in this course? I already mentioned this very superficially. There's some theory, of course. We're operating with 3D objects and scenes. We're also operating with a translation from 3D to 2D, and in between here there's a lot of math. You know, movement perspective. I could speak about math here for a very long time because the background here is very mathematical, but as I said before, it's no point in pushing that too far. It's more important to get this hands-on. But I will try to, we have to learn some concepts, and I'll try to explain them as geometrically as I can so that you have an idea what they are. Frameworks. There are different frameworks for graphics programming. The one we will use is OpenGL. It has to do about its appropriate level as well as being platform independent, which is a very nice thing because if this runs on different platforms, if you learn to program this in one way, you can have it on other operating systems as well. So once you have it set up properly, then you basically use the same sort of coding, which is nice actually. We have also other ones, SDL, which is a two-dimensional thing. We will not use that one, I think. DirectX Windows based, as we talked about earlier. Vulkan is a low-level version of things. Yeah. Another thing, integration. You know, this. Of course, you meant to use this in a broad perspective. I already talked about some applications, but of course you can, you know, combine it with some general-purpose programming language to illustrate something, as I said, or you know, deal with input interaction, user interaction, like in a game, for example. So these will be things we will look into. Yeah, disciplines. Goes without saying that computer science is a discipline here. Programming, APIs, code management, mathematics, geometry, matrix multiplications. There's also a little bit of physics in there, in the sense of how light bounces off surfaces, you know, opacity, whether you have absorption or something passes through, transparency, reflections, and those sort of things. Object positioning, shadows. So these are it's a sort of broad set of disciplines in this course. But I think everything is very visual, so it's quite okay to get the grasp in that sense. Any questions? Comments? Okay. Yeah. So today we have about half an hour left. I will talk about some terminology, common terminology, and some image formats. Now, image formats is really not a part of the course in a sense, but we talk about it because you will run into them, so you just know some of what it is, basically. Okay, terminology, pixel. That's something I guess you know what is. Fundamental picture elements. Pixel is basically the fundamental for textures on some surface or object, basically. The smallest part of that, which can be, for example, something you tessellate the surface with. If you have a tile, for example, then that can be a basic texture element. So basically, when the surface is textured, this is the basics of that. It does not necessarily need to correspond to, or it usually doesn't correspond to single pixels. If you have some object and you zoom in on it, then the texture element will become larger and larger and occupy more and more pixels. If you shrink your object, then you know the texture element may actually disappear within 1 pixel, and so on and so forth. So there's a difference between them. And just to make things confusing, it's also referred to as pixels as well. Okay, sprite. Anybody knows what that is? Simply put, it's a bitmap picture that you put onto the screen. It may be some object that moves that you interact with. Tiny thing in a game, the player, for example. Something that moves in a landscape. And this has a palette of its own, which is basically the area of colors that you can that you can put onto it. The next three ones I think I will explain a bit more on. Blitting, parallax, and projection. Projection is quite obvious. How do you project 3 dimensions into 2 dimensions, basically? That I will talk about that later. Blitting is basically, when you make a scene, it consists of different layers. So you have the background, like here, then you have something in the foreground, you have another layer, and so on and so forth. When you combine this into one scene, and you override something with the others. For example, when you're looking from here, this will sort of cover parts of the background. Then you're basically blitting that with this surface. So basically, is it about? I can show this drawing. So you basically put things on top of each other. Then what is behind it is overridden by what's in front, and so on and so forth as you go along. And then you usually say, like this explains that you render over what was there in the first place. And that is, of course, what you end up presenting on the screen is what is in that part of memory. And then you have parallax, which is this alleged movement. Oops, maybe I have the right slide. So when you have these different layers in a scene, and you're moving in this, then these different layers will move at different speeds to make it look natural. This is how also your vision works. So next time you're sitting on a train, for example, try to look at how the far background moves compared to what is close to you. You will see that what's close to you, if you, for example, the train moves much faster than what's more remote. So I can illustrate this to just yeah. So here you see scene with several layers, one layer behind here, another layer, third layer, fourth layer, and then the parallax movement is the different speed at which this moves. So you see the background is moving much more slower than the front layers, and so on and so forth. So that's parallax movement. Of course, here you move sideways. You may move, different ways in the scene. Here is another one. You see the background here is moving much more slowly than the foreground. The camera angles may be a bit different, so here you see the background moving differently than foreground. Here, same thing. So depending on how the camera moves, you will see these layers moving at different speeds. And if you want to make something look realistic, this is something you have to take into account. I always like to ask the question, why is this the way? Let's say you're sitting on a train and these different layers move at different speeds. Why did they do that? Because you're basically having a fixed speed. You're having a fixed speed on that train. What the different layers seems to move at different speeds. Yeah?
Because speed is distance over time.
Mm-hmm.
And at longer distance, the distance will seem smaller.
Yes?
And because it's smaller, it's still going with the same speed.
Yep.
And it will take the same time to read, but because of the smaller distance, you will perceive it moving slower.
Mm-hmm.
That's my idea.
Yeah, sure. So, but then the follow-up question is, why does it appear smaller at a distance?
Why does it appear?
Yeah.
Okay.
Because what you're saying is absolutely right. But then again, why does it? Because take this object in 3-dimensional space. It has the same volume.
Yeah.
Of course, but I move it more remotely, it shrinks.
Maybe somebody can continue. I need to think about this.
Yeah, sure. Who was first? I don't really know. Okay. Yeah. Okay.
This has something to do with the fact that when an object is further away from you, the light it reflects back to your eye is smaller.
Mm-hmm.
This is why the white appears to be smaller in a distance.
Well, not exactly. You wouldn't grow bigger though if you dim the light, for example. You would still be small at a distance.
Yeah, but the difference is that the same angle of light is still reflected. If it's dimmer, it's just less of the light, right?
That's true. I mean, you get less because it spreads in all directions. But it has something to do with that. If you think about things going in cone, it's not exactly the light, but it's how your vision is sort of increasing, right?
Yeah.
Outwards, like a cone. So you have, or did you have any?
That's what I was going to say. It's about the angle that it forms with your retina.
Yeah, exactly. So.
It's the percentage, because farther away you see more, and that's just a smaller percentage of the whole thing that you see.
Yes.
So it appears smaller in reality.
Yes, exactly. Because you see in a cone, right? So everything that is far out here, if you take this and you move it out, it will appear smaller and smaller and smaller and smaller. And that is, of course, because you are projecting through a point and then back to your retina, you will see this actually upside down. This is actually something called projective geometry. This is how your eyes work. We'll get back to that in later lectures. But it's good to think about these things because they're important when you try to model this scene to understand what is going on. Good. Yep. So you got the idea of parallax, I hope. Let me see where were you? Yeah. There's these more technical terms, OpenGL related things like vertex buffer object, vertex area object, vertex buffer and so on. We'll talk more about those later. But basically vertex buffer object is an array of floats. And these floats are basically determining nodes in a triangle, for example. And then a collection of these buffers you have in an array. And this is what the GPU is processing, basically. But yeah, I'll go to details there. Shader, I can mention. Anybody heard that expression?
No.
Okay. So basically, we program defining a rendering style. We will program these things later. Yeah. So this. Yeah, this is really important to mention in the sense of use of memory and those sort of things. In the old days, when you made games, you didn't have the sort of memory and processing power you have today. But still, you had some scenes that were moving. Sometimes you didn't. One way to deal with that is that you just had a fixed scene where everything went on, and then the characters moved in this fixed scene. Or you could have a much bigger scene in which you had the possibility to move the camera around, and then different parts of that scene would appear in different places. This is how they coped with memory limitations. You heard about side scrollers, by the way? Yeah. I mean, today this is really not that sort of a big problem, but I think the message with this is to always think of what you really need to display or not, and think about how you make your application the least demanding, because although you have more memory and processing power, the applications are getting more and more demanding as well. You do things in 3D, you have a lot of fancy things going on, and the more you think about avoiding over-processing or determining bottlenecks, the more fancy thing you can do without things just running into to a halt. The idea is to think about this early on, I think. Any comments? Okay, so I'll just wrap up. The last thing I'll talk about today is image formats. Coarsely, you can divide them into two. It's raster formats and vector formats. Raster formats are basically those who are pixel-based. So basically, they are discrete in nature. So they're sort of like very well fitted to be displayed on the screen. The advantage of those is that you can compress them, for example, or you can compress them in a lossy way, in which you can make smaller files, particularly if you have very detailed scenes, for example. Vector formats has the advantage that in a sense things are represented by vectors and not pixels, so you can blow them up, zoom in on them, and the objects in the scene will appear just as clear. So that's the disadvantage, is that you cannot really compress them, at least not in a lossy way. I think you can do it in a lossless way, but not lossy. They will of course also be rested because they have to be put onto the screen, but that's sort of like the last step. That's why I write that, you know, these vectors are basically defining continuous structures. You know, paths, you know, points, lines, those sort of things. And the last, they're not really discretized before they're sort of put onto whatever screen they're going to be put onto. So examples on rastered is PGM, PNG, TIFF, JPEG, GIF, vector formats, EPS, X3D, scalable vector graphics. You probably heard about some of these. Okay, so yeah, we'll just go a little bit more into details. You have this old simple format. We won't really deal with them. I think you have this old one grayscale, just plain text. So you have a bitmap, which you probably mostly know about. Then you have these ones which you can do lossless compression, which is PNG, TIFF, GIF. Then you have, this is a bit dubious to say it's lossless because you actually lose some information in this one, but that doesn't have to do with the compression, so I chose to put it on the so-called lossless compression. And then you have those who do lossy compression. Do you know what the difference is? Yeah?
Between lossy and lossless, right?
Hmm?
The difference between lossless and lossy,
Yeah.
right?
Yeah.
You can retrieve the lossless compression, you can
Yes.
retrieve the original image,
Yes.
which you cannot with lossy compression because you lose some main information about the image.
True, true. Indeed. Any other comments? Okay, same, yeah. So, you know how you can do compression losslessly?
Losslessly.
We can take repeated information and just let them know that it's like all of these bits are going to be the same. You don't have to be redundant about it. You just
Exactly, yes. So it's all about redundancy. Redundancy is basically something you can take out. You don't have to transmit it, you don't have to store it, because it's basically given itself. So for example, if you took a picture of this blackboard and saying, then you could take that pixel, and instead of sending each and every pixel here, you could look at the difference. For example, what is the difference from the first pixel? That will be much smaller, and then your amount of data will be much lower, and as you say, you will not lose anything. You can just add that on at the receiver side, or when you open the image file. So yeah, and lossy, as you said, is also about removing information, and when you remove information, you cannot retrieve it. In this case, you can. The reason why you would like to look at lossy, for example, if you have very detailed pictures, it's very, very hard to find any redundancy which you can remove. Then it's an advantage to sort of use lossy compression. And you can also do that without it being too disturbing, because there is a lot of things our vision cannot detect. Right? These are called irrelevancies, basically. So if you remove information but our visual system can't detect it anyway, it doesn't really matter. So you try to emphasize on that. And if you do that, you can reduce the file size quite a lot without actually distorting the image too much. So you keep the most important parts, so visual parts for human, basically. And apart from that, you throw away as much as possible. So JPEG is an example that does this. This slide is a bit dense, sorry for that. It's one of the was it one of the first that had lossy compression?
I think so. One of the formats in any case, so non really. It's openly available, more broadly accessible. I think there's some proprietary, formats that were highly specific to particular industry or so on, but this was broadly for camera scanning and so on.
Yeah, so this was built from basically trying to model what our vision can detect or not. So it's Yeah, just some information. It has a 24-bit color range, which means that you have 2 to the power 24 different colors. Lossy, of course, that's one of the things this is about. And then, of course, you can get quite small file sizes, because as you progressively compresses, of course, the quality gets worse and worse, but you also you reduce the file size. I'll show you one example soon. File format is quite straightforward. You have a header that identifies the format, some compression tables, which has to do about the lossless part of the compression. You need to sort of identify what sort of method you use. Quantization tables is important. This is basically how do you discretize your image or the different frequency bands. And then, of course, you have the content, which is added on afterwards. And then you have also the possibility for some application-specific data. Now, there is a thing about brightness and also high frequency when it comes to human vision. So, for example, if you have a very light surface in front of a very dark one, then reducing the difference between them in brightness doesn't really matter much for your vision. It will appear more or less the same to you. If the difference is smaller, like if you have a shadow cast on the surface, for example, then it matters much more. So you will try to reduce where your eyes is detected. As I said, this is removing irrelevant information first. And also very high frequency content is usually not as sensitive, depending of course on the scene, as for example low frequency content. So what you do in JPEG is that you split the image into blocks, for example 8 by 8 pixels, then you transform them into the frequency domain using a version of a Fourier transform called cosine transform. You have know about this?
I know about the Fourier transform, but not the method.
No? Cosine? It's basically that instead of using the complex exponential function, you use cosines. Yeah. Otherwise, it's the same principle, basically. And the point is that when you do that, you will split your image into different frequency bands. And basically, then you can allocate the bits you have available to those frequency bands where you have most of the energy. And that's usually the most important ones. Usually, on a typical image, you will see that the energy can go something like this. So the lowest frequency has the highest energy. It's not always like that, and then, of course, it sort of goes down. But it depends on, this is just one example, it depends on the image content. And then we sort of allocate most bits to the most energetic part of the spectrum. Yeah, so that's coarsely how it works. And this is just an illustration of what it does. So if you go from a file size of 725 kilobytes to 250 kilobytes, you do not really spot any difference at all. So it's a huge reduction, but still you don't really see the difference. If you go all the way down to 10%, like 37 kilobytes from 725, which is a very huge reduction, yes, you start to see some artifacts, some color changes here, for example, some block artifacts here and there.
What's artifacting?
Hmm?
What's artifact?
Yeah, I should probably be a bit more precise with words. It's basically, here it's blocks, basically. Something that appears in your image. I mean, an artifact may be something that should be there. In this case, it's something that shouldn't be there. So when I say artifact now, it's something that shouldn't be there. And typically in JPEG, you see this block patterns appearing. And this has to do about the fact that when you use fewer and fewer bits, you will be able to represent less and less of the spectrum. And when, let's say, in the end, you will just represent only one frequency, which makes this into a grayscale block, and then may not match as due to the neighboring block, and then you start to get these features here, or artifacts that you don't really want. But given the fact that you have reduced from 725 down to 20 kilobytes, it's a huge reduction. It's not too bad, so it's considered to be okay. You have varieties of this that doesn't use cosine transforms, but they use something called wavelets. If you heard about this, it's basically instead of having, fixed functions like that, you have these sort of functions that takes off with time. I won't go into details, and it's not important for the course. But if you use that one instead of this, you can actually compress almost down to that level, and it looks nicer. So there are newer versions of this, but I think this is the one that is most widely used. there's a lot of possibilities. But as I say, not too important for the progression of this course, though. Yeah, a little bit about vector formats here. I try to illustrate what the difference is. So if you have this bottle here and you have a rastered image, you blow it up, you will get this, pixelized sort of block-like artifacts in the picture, making it hard to see what it is. If you use a vector format, then it's clear as day. You can basically read what is there, and that's sort of like the point about it. And this is because everything is represented by vectors and sort of like nodes and curves in between them define the image, not particular pixels. So that math sort of does the thing for you. You have one I would like to talk a bit more about, this scalable vector graphics. It's because it's some extensions there. So it's more or less like any other vector format, except that you also have the possibility for interactivity and animations, which makes it important for this course. And of course it supports various algorithms like paths. You can include bitmaps in and so on and so forth, which means that you actually get a rasterized image in a vector graphic file and so on and so forth. You heard about this sort of image files? No, to you? Yeah? Yeah, sure.
How would you make a picture with SVG?
You mean a natural picture?
Yeah.
Yeah, that's a problem, because when you take a picture, you use a camera which is already pixelized, so then you basically have a raster format. So this is more into it I think this is more convenient when you create graphics on the computer, basically. Of course, you can, of course, I think you can also vectorize these ones, but then you will have some of the same problems, but because they will have fixed resolution from the camera itself. So I think this is more for computer-generated graphics than it is for taking pictures. Or I believe that's so.
Yeah. So literally, you construct drawings out of parts of nodes and so on. You can embed pictures, but fundamentally, it's just for charts, figures, scalable elements. And that was particular made with respect to web technology. For example, you have different platforms. You want to display something, right? It needs to scale up and down quite flexibly and still look, roughly the same, basically. So, and it's an open format. That's really nice, right? Because you can actually, if you have an SVG file in the browser, try to find one. I'm not sure if you're showing one, but if you right-click and look at this page source, you basically can see how the source file is constructed. The nice feature there is that you can actually also modify it, right? So you can actually change the coordinates, for example, of nodes and so on, which you of course can't do in rasterized images, right? You can't just take a picture and then change the orientation of the rocks, for example, you just saw there, right? So those are they are for slightly different application purposes, but it's important for you to understand that those different formats exist. And that's not just images, but there's difference in terms of rasterization with a vector format and so on, different forms of compressions and so on. So this one is, for example, inherently not compressed. I think there's a version called SVG-Z.
You can do lossy compression on.
Right, so it's simple zip compression on basically. You have it. That's right. So it's basically like a text file. Think about it like a text file, human readable, and then it's potentially compressed, but very, very inefficient compared to, for example, JPEG. So it's depends on the objective, really, right? So.
Yeah, because if you try to do lossy compression of those, they would fail. So you have to. It's only redundancy you can take away.
Exactly.
And get away with it.
Good point.
Yeah, I should have shown the file probably, but I'm running out of time. I have to give some more information towards the end. But I think that you did that last year, maybe. I have some few minutes left, so I think I'll just have to wrap up the resources and lab and information, those sort of things. Books and resources. If you really like to read, sit down with a book and look through and understand things from a more fundamental perspective. This book is nice. It's very large, but I think you said you need to read about 200 pages.
For the whole semester.
Yeah.
That's the basics and the relevant part. Everything else is more like in-depth or advanced techniques.
So.
And like 50 of the pages are on mathematics that you're going to need for graphics. So technically it's only 150 pages on programming.
That's a good deal, right? 150 pages on programming. That's a. Come on, guys, you should go for it. That's so easy.
I think on Amazon it was about 450, 500 grams, something like that.
Right.
Is it written in the GitLab wiki what part of the book are covered every week?
No, I mean we haven't really we haven't linked this to any particular book. These lectures that should probably be, that could have been the case, but for example, this one contains so many things that we wouldn't really do that. But yeah, I guess it would be an idea to maybe point every topic to a specific chapter in the future, or maybe during the course now. Yeah.
It may be more practical, I mean, given the nature of the lectures and the very applied nature here, that this pointer would be done with respect to Anton's
exactly.
tutorial.
Yeah.
Because they're really nicely, and they are free online, I recall, and the ebook, you basically support the author for doing a really good job. He's teaching somewhere in Ireland, I'm not sure, you would call it Dublin or something, computer graphics. He has written this set of tutorials basically, and they basically sit quite well within this course, right? A lot of issues, lighting or modeling and so on. This is really.
These are free. You can go through
Yeah.
them online. If you do that, you will get some grasp of what goes on. The problem with them is that you won't get much information around it. That also go through this book. You can also read through, which is connected to this one. But if you like more information, understand more about the surrounding framework, then
Sure.
for example, you can go there. But you can also get away with this and get through the course, basically. Yeah.
Do you know if the book is in the store?
No, I don't think it's there. I was there a little bit before Christmas, so I ended up ordering it. So no, I think that's because it's not an official book for the course. It's something we recommend more or less. So you have different recommendations. You can choose yourself if you want to spend only €6.5 to go through that, do that, or you can download these for free and go through them. There's a lot of text in that.
Yeah.
Also, these ones, some of them are a bit outdated, but they also have a lot of explanations around. But it's only the least information you need to be able to put up certain things. If you want more information about how this is structured and understand a bit more about it, also get a little bit of input on the maths, and you can do that one. So it's a bit up to you what you end up doing, what you sort of prefer. Yeah, so these tutorials are nice, recommendable. This, as I think you also mentioned in the beginning, is a nice YouTube video where they explain basically most of what we need to go through. And these people are nicely explaining, so it's a 2-3 hour movie, but I mean, you watch it once and divide it in sections, so you will get some nice information. Sort of like a look ahead. Yeah. Okay, so very fast. Updating drivers, very important. Yeah, we should run these versions OpenGL 4.3 and beyond. We will also do a lot on this on the lab on Thursday. It's about setting up OpenGL on the computer and getting this up and running. We will also then draw some triangles once we've got it up and running, just to test everything is fine and get a little bit accustomed to this OpenGL framework. Also some information on driver updates, code fragments and so on to get windows up and going, and so how you create a window in OpenGL and so on and so forth. It's explained a bit in this tutorial. It's a lot of things that is a bit outdated and a lot of things you don't need to do, but you'll get a grasp of it. If you start reading, you'll see. If you want to start to do this on your own before. But we will go through this in the lab and help you out if you get into some big problems. But very important, update your driver. That's important, so you can run this thing. We will also have a demonstration on Thursday to begin with that. And I think if we need more time than Thursday to pull this through, we will also take next Tuesday and use that to make your machine run, because you have to get this up and running. If you don't do that, you will not be able to do anything, and then you will be stuck and you will sort of not be able to pull this through. So it's very important that we make this run on your computer. Do you all have a computer that you can by yourself?
Very important.
Everyone? Yeah. So we'll try to make it work on that one as soon as we can. Hopefully, I think that should go fine. Yeah. Next week, C++. That's next Thursday, by the way. So you know. Yeah.
Perhaps one final word on tutorials, right? So I mean, there was a long list of tutorials. First of all, those are kind of resources that we consider to some extent, worthwhile following. There's way more out there. The risk is many of them. So OpenGL has been around for a while, right? So and that is we're talking 20, 25 years. So the challenge is there. A lot of tutorial material that's out there is a bit outdated, oftentimes referring to OpenGL 3. Stay away from those, right? They're not bad at all, but point is they are pointing at an old version of OpenGL. So you find very different ways, for example, of setting up lighting there from what you are going to be taught in this course, right? So be very, very mindful. That's why we pointed to some tutorials, even though there's an abundance there. We encourage you to be proactive and look for tutorials and solutions and so on yourself, because a lot of it is trying and see how it works, a bit like experimentation on your own code and your own system. But bear in mind OpenGL 4 onwards. That's the key thing that you always want to watch for, else things might have changed significantly and suddenly your code doesn't run. You're wondering why this tutorial doesn't run in conjunction with code you have potentially been given by us and so on, right? So it's really important that we entrench that often enough, right? So a few things: get your graphics driver updated, remember OpenGL 4 onwards, nothing older than that. That's the few things to bear in mind.
Yes, indeed. And I think this year is also a comment by Carl that we may make some smaller assignments that you can do to understand a little bit more of the framework you put up, so you just don't have it there, boom, and then you start to deal with the little parts of it, sort of make it a bit more step by step, in addition to the labs, that is, which is sort of things you can do at home. Yeah, I think that's it for now. Then there's a lab on Thursday at 12:15 in A146 this week, and then next week the thing switches.
What will this recording be? When will this recording be put on?
Oh, it's already linked, I believe. It's in the playlist.